This conference will now be recorded.
Very good morning, students.
This conference will now be recorded.
Very good morning, students. Today we'll be completing this chapter, Kinetic Theory of Gas, by discussing a single topic, mean free path, and we'll discuss few important numerical problems on kinetic theory of gases. So then let us start our business today. Mean free path, you might have already learned in your courses in chemistry, but still we'll discuss here in terms of physical view, and this has actually important uh, numerical problems on this mean free path in various competitive exam. So we'll learn it nicely and try to solve problems on this. So as I said, mean free path. So mean free path, before we learn what is mean free path, let us say what is free path. What is free path? Actually, this is related to a system where there are statistical number of systems or particles. Statistical in the sense there are lot of number of now like a large number of systems or a large number of particles here. So if I say kinetic theory of gas, mean free path in kinetic theory of gas, then I just consider that there is an ideal gas which has a large number of molecules, gas molecules. And what do they do? Gas molecules are not at rest at all. They are actually randomly moving here and there inside the container. And in that process, we had discussed already that in that process, these gas molecules, they will actually collide with each other, and they will collide with the container, wall of the container also. So that is the reason we get pressure. Okay, that is the reason gas or liquid exert pressure. Now we know the molecules of a gas are in a state of continuous, rapid and random motion. Let me write some words. So gas molecules are are in continuous, rapid and random motion. They are always in this state, in the state of continuous, rapid and random motion. Okay, random motion, how random it is? Suppose I have few molecules like this in a particular gas. So each molecule will move randomly. Okay, and in their course of motion they will collide with each other. They will collide with each other, and after collision they don't stop. Okay, so they don't stop after collision. What do they do? What do they do after collision? After collision, suppose I have one molecule here, another molecule here, another molecule here, another molecule here, some molecule here. So what the molecules do? They will collide with one guy, then they will change their direction as well as the speed. Okay, and then further they will collide here, and then further it will collide here. If some molecules are here, it will go here. Okay, after colliding here, it will come here. Again, it will come somewhere here. Okay, maybe if there are molecules somewhere here, it will collide here. Again, it will collide here, collide here. Okay, like that, it will be a zigzag motion. But one good thing you can look here to specify or to analyze this motion, nature has given enough hint for us or enough opportunities for us. Look, between two successive collision, after colliding with this, a molecule collide collides here. So between two successive collision, there is a motion in straight path, and with an average velocity. Okay, in between two successive collision, molecules traverse a straight path or straight line with an average velocity. This path, the straight path in between two successive collision, is called free path. Free path. Okay, and the velocity, average velocity in between two successive collision, this is called free velocity. Okay, okay, so mean free velocity anyway. So this is free path. Let us stick to path. And if we take, see, there will be a lot of collisions, right? And there will be many such free path, many such free path. Okay, suppose there is, if I say this path is lambda1, another path lambda2, okay, another path lambda3, like that. If I just give some name or take the length of this path, lambda1, lambda2, lambda3, then if I know, if suppose there are n number of collisions, then I have a lambda1 plus lambda2 plus lambda3, like that, that you can just add the numbers, sorry, add the path. Okay, mean you can add the path and then divide with the total number of collision. Here it is 9. There are 9 collisions. So this will give you a quantity called mean free path. Either you can write in terms of uh, bar or in terms of bracket. Okay, whatever it is, but the meaning is same. So let me show you actually a very good figure which I have borrowed from some source. So here, look here, the mean free path. See, these are the state path, as I said, between two successive collision. Between two successive collision, this is one state path. Between these two successive collisions, you get another state path. So these state paths are called free paths. And if I take the mean of all these free paths, then it is called mean free path. So if I uh, define what is mean free path, and one thing you should remember that while uh, the molecules are moving in this free path, along this free path, there will be a mean velocity or an average velocity. With average velocity or uniform velocity, it will move. Okay, so what is the meaning of mean free path? So mean free path can be defined as mean free path mean free path of a gas molecule is defined as is defined is defined as the average distance average distance average distance traveled by the molecule traveled by the molecule molecule between successive collision. Okay, so this is actually mean free path. As I said, if there are length of free paths are L1, L2, L3, L4, sorry, lambda 4. If these are the successive mean free path, distance of the mean free path, sorry, free path, distance of the free path, distance of the straight path, then, sorry, this is 2. Total number of collision. So this will give you lambda bar, which is called mean free path. So lambda 1, lambda 2, lambda 3, lambda 4, these are actually free paths. There are many zigzag free paths. Okay, this is actually mean free path. Now we'll derive the expression for mean free path. Let me send this off. We'll derive now the expression for mean free path. In order to derive the expression for the mean free path, we have to make some assumptions. Okay, we'll make certain assumptions. Let me write derivation of the expression for mean free path. Okay, so to derive the expression for mean free path, we have to make some assumptions. So first assumption is that all the molecules are all the molecules are spheres of diameter d. So all the spheres, so the gas molecules are treated as sphere, and all the spheres have diameter d. Second postulate is that all the molecule except the molecule, you can see here, except the molecule this, except this molecule, all other molecules, let us see, are at rest. Okay, so these are two conditions. One is all the molecules except A, all the molecules except A is at rest. Okay, so these are two assumptions. Now, see what we have to find out. We have to find out the expression for the mean free path. Okay, let me tell you what we need to find out here. We have to find out the total free path. So here, let us say in between two successive collision, a gas molecule has an average velocity this in between two successive collision. Okay, in between two successive collision, it has average velocity v bar. Okay, now these atoms, see these molecules, they are very very tiny, but they have finite size. Because of that finite size, see, if I have a molecule over here of diameter d, when this molecule moves along a path, in a straight path, you look the straight path, along straight path, it will collide with the molecules which have their centers at 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 d distance away. Okay, see the d, this is d by 2, another d, so this is also d, and this is also d. So I have considered the gas molecules to be of spheres. As you see here I am taking a representative gas molecule which has a diameter d, and all other molecules also have the diameter d. Now what happens, we have to see the collision parts. So when this molecule A travels in a straight path, it will collide with those molecules which have their centers d distance away. Look, at least their center should be center to center distance will be d distance away. Look, if this molecule comes here, it will be like here. So this is d by 2, this is d by 2. Their centers are at d distance away. When this molecule comes here, so there also there will be. So when the gas molecules starts moving in a straight line, it will have a collision with those molecules which have the center to center distance as d. Now all these things are fine. Now let us consider a real situation that at time dt, it will obviously collide with all molecules within the cylindrical volume. See, if I want to calculate the number of delta t time during delta t time, you look here in this figure. If I suppose that I want to calculate the number of collisions, number of collisions in delta t time. So number of collision in delta t time, if you want to calculate, you have to find out the volume. So this will give you the volume of this cylinder. volume of the cylinder, volume of the cylinder of length, cylinder length of the cylinder will be V bar T, and area pi r square D. Okay, within this volume, pi r square means P, let me, sorry, so this will be pi d square, pi d square into V average into delta T. Okay, this is the volume of the cylinder. Within this volume, how many number of molecules comes? They will undergo a collision with the molecule A over here. Okay. So how many? So this is pi square. Okay, so this is the volume. So this is the volume of this cylinder, and we have to find out the number of. So you look, if you have less number density, then collision probability will be less. If the number density is more, then there will be many more molecules like this, and there will be a collision obviously. Okay, so ultimately the number of collisions will depend on the number of molecules contained by this particular volume of the cylinder in time dt. That is the volume of the cylinder. So pi r square, sorry, pi d square, this is the pi square, this pi d square V average delta T. This is the number of molecules per unit volume, but if there are n number of molecules per unit volume, so n pi d square into V average square. Okay, so the number of collisions, look, number of collisions we have got already. Number of collisions, so number of collisions will be given by pi d square, pi d square into V average A dt, and here there will be n multiplied, because this is the number of molecules per unit volume. Now if we calculate the rate of collision, so this actually happens in delta t time, collision in delta t time, then rate of collision, that means rate of collision. So rate of collision can be found out, total number of collision divided by Actually, rate divided by time, delta t time taken by delta t time. So total number of collisions divided by delta t. So this will give you, the total number was this divided by delta t will give you pi d square, then vn dt already you have taken, we have just taking, you can think of derivative also, you can think of division also. So n pi square, n pi d square v into n, this will give you the total number of rate of collision. When the rate of collision is rate of collision, then it is pi d square nv. Okay, so this is rate of collision. Now when you know rate of collision, then to get the time, it is not a problem. So we can find out the time of collision. So that is 1 by tau is equal to number of collision, sorry, 1 by tau number of collision, or the duration of the collision. This is the time. So 1 by tau, that is the time it takes for that many collision. So if we have written that as uh, this is the rate. Suppose if I write some quantity d, suppose dn by dt, so this implies n is equal to dn by dt is equal to any quantity. So how to find out dt will be this, okay, like that. So in this case, if you take the reciprocal of this rate of collision, number of collision, if you just take the reciprocal of that, that will give you the time it takes to collide those many numbers of collision, or suffers those many number of collision in dt time. Okay, so therefore if I write this, let me take time. So we have 1 over rate, so that will give you the time. So 1 over rate we know already, pi d square vn. Pi d square, 1 over rate, that means pi d square then n v average. Okay, so this is the expression for the time it takes to have this many collisions. Now if we know the average velocity into time, that will give you the lambda, mean free path. Okay, so this is So B average will go off from up and down. So you will get, so pi d square and n. This is the mean. I'm sorry, I have written double mean free path. Okay, this is called mean free path. So this is the expression for the mean free path. And this mean free path, if I consider that all the molecules are not at rest, then this mean free path expression for the mean free path would be okay. So this, so here will be there an n. So lambda bar is equal to 1 over root 2 n pi into d squared. Okay, so I'll just write the expression. Mean free path expression is 1 by n pi d square. N pi d square. So this is the expression for mean free path. Now, what are the factors on which mean free path depends? One is wavelength. One is mass. If I see in deep, then the diameter, temperature, so these are the factors on which mean free path depends. Now we'll move on to few numerical problems. Just a minute, we'll take up few numerical problems from here. So okay, here there is a problem. I'll write. Okay, madam, are you able to hear now? Is it okay? Can you respond in the
Yes, yes,
message?
yes.
Okay, okay. Suppose the RMS speed sorry, the question is like this. At what temperature? At what temperature at what temperature RMS speed, root mean square speed of an atom in argon of an atom in argon gas, let us say AR gas, so at what temperature is the root mean square speed of an atom in an argon gas cylinder equal to RMS speed of a helium gas at minus 20 degrees centigrade. So atomic mass of argon is given as 39.9. This is atomic mass, say argon, and atomic mass of helium is given as 4 atomic unit. This is also in atomic unit. So this is the question. At what temperature RMS speed of both will be argon will be same as the RMS speed of helium at minus 0 degrees centigrade. So to solve this problem, what you should do, you should remember the root mean square speed expression for root mean square speed. So that is given by 3RT by M. So this is the expression you should remember. Okay. Suppose I'll write this for both. And this temperature you should be remembering that this is in absolute scale. So V RMS for argon divided by, let us just do this, divided by V RMS helium. If we take the ratio first, what will be, see, according to this term we'll write anyway 3R, and 3R is constant. So for argon 3R M into argon, so M argon, and then T is actually the temperature in absolute scale. Okay, I'm writing just T like that. So T1, suppose this is T1, which I have to calculate, I don't know, but for helium, you know, root 3R by M helium and then T2, suppose. Okay. So when these two will be equal, that means this side, suppose this side is 1, then what will be, so T2 we know, what will be the T1 temperature? Let me go to the next page. So we know we have got root 3 R T2 by M helium is equal to root 3 R T1 by M argon. See, I have to find out T1. I can just square them out both sides. So you will get 3R T2 divided by, this is M argon will come here, and here it will come 3R. Okay, 3R goes off, and there will be obviously MH also, He. So T2 is actually minus 20. Minus 20 means in absolute scale, this is, you just this is the temperature T1, sorry, T2 in terms of absolute scale temperature, and this MAR, that is given 39.9 divided by helium is given as 4. Let me take this as 40. So this will give you 10 roughly. So this will give you 10. Okay, and from here you will get 253 Kelvin. So this, if you want to write in degree centigrade, you have to add. If you want to keep it in, oh sorry, this is already, we have got, I'm sorry, we have already got this temperature. So in Kelvin, 253. So the temperature must be 253 Kelvin, and there is another term along with that, this factor will give you 10 into this Kelvin. So 2530, nearly 2530 Kelvin. Okay, 2530 Kelvin. So that is the correct answer. Okay, so this gives the correct answer. So mean free path, expression for mean free path, expression for average, all this you have to remember. Expressions, at least the people who are trying to various competitive exam, they must be remembering this formula 3RT. So this is the mean free path expression you should remember, and then only you will be able to solve this problem. We'll take up another problem in this chapter. This say, okay, so see, this problem is very, very important. Suppose there is a monatomic gas. There is a monatomic gas. You have to find out the specific heat of a monatomic gas. Let us write okay, let us take a question itself. There is a nice question. Question is that should the specific heat of monoatomic gas should the specific heat of a monoatomic gas monoatomic gas be less than be less than equal to or greater than that of a diatomic gas. At RT, room temperature. You have to justify your answer. So the question is whether the specific heat of a monatomic gas will be less than or equal to or greater than the specific heat of diatomic gas or diatomic molecule at room temperature. That means temperature doesn't change. So how to solve this problem? You have to find out the specific heat. In this case, there are two specific heats. One is Cp, another one is Cv. Since the temperature here actually, see specific heat will compare for this to is Cv for monoatomic gas, and what is Cv for diatomic gas. Cv means molar specific heat at constant volume. Those two we will calculate. Okay. So to calculate this, what are the things you should know? We know Cv is equal to dq dt. So dq dt and you have to find out actually the total energy C for Cv dq will be exactly equal to du into dt, and this du you have to find out. I hope you remember we have to find out du as average kinetic energy of the gas molecules. So how did you do that? Actually, we had to learn what is degrees of freedom. Then, after knowing the degrees of freedom, each degree of freedom will share half of cavity energy. So we have to first write down 3n minus L. 3n minus L with this expression. See, for monoatomic gas, in this capital N is equal to 1 and this L is equal to 0. So this will give you, for monoatomic gas, it will give you 3. But what about diatomic gas? There are two things. Diatomic, okay, so you have for diatomic gas 3 into 2, so it will give 5. 3 into 2 minus 1, dumbbell shape you can consider. So degrees of freedoms are found out. Then what is the total energy. So 3 by 2 kBT, then 5 by 2 kBT. Okay, so if you add, okay, so this is, I'm sorry, actually, uh, you have to find out the comparison. Okay, but these are two different gases. So for monoatomic, you have got U is equal to 3 by 2 kBT. Then CV for mono will be 3 by 2 kb. What about that diatomic gas? For diatomic gas, it will be actually 5 by 2 kb. Okay, 5 by 2 kb. All right. So again, if you multiply, this is actually molar specific heat per molecule. But if you write Na here, then 3 by 2 R, and here also it will be 5 by 2 R. So for diatomic gas CV mono, you get 3 by 2 R, and CV diatomic gas 5 by 2 R. So this is nearly 1.5 R. $2.5 R. So basically, this is at room temperature. So the specific heat for a monatomic gas is less than that of the diatomic gas. Okay, so we could do only 2 problems. I'll do one thing. In the next class, I'll take up at least some 10 more problems. Okay, quickly within half an hour, and then another half an hour we'll start a new chapter if possible, or maybe we'll continue with the numerical problems part 2 for this chapter in the next class tomorrow, and then we'll start a new chapter. And there in these numerical problems we will take up problems from various parts like equipartition of energy, as I had discussed today, this problem specific heat. Then we'll take Maxwell velocity distribution, and then we'll take questions from mean free path, etc. Basically we'll take up questions from various competitive exam. Okay, today I'll stop it here for and let us meet tomorrow. Okay, bye for today.